Hey guys, I hope everyone's healthy and everything's going well. We are moving on today to 29-4. It's on page 457 of your book. Let's take a second and get that open. You can see some learning targets there. You can also see this. We're basically doing a lot of the same stuff we did on Monday, but you're just going to see today that we're going to have to, in order to analyze the graph better, we'll have to do a sum or difference of two or more rational expressions. Okay, so we're working on common denominators first, and then going on to all the graphs we did on Monday. So let's take a look at one here. I'll call this example A, and you see this is the function we have going on. And you see, unlike Monday, it's not one big fraction, not one big rational function. It's actually subtraction of two rational expressions. So the easiest way to handle this so that we can use all those techniques we used on Monday is to give these guys common denominators, okay? So this should be review, right? We did this on Fluency Test 5. We worked with all these guys and gave them common denominators. So I'm going to write this first one out. There's a GCF in the bottom of that second fraction. So then I need to multiply this first piece by x over x. Because I'm giving common denominators, I have to do the same thing to the top and to the bottom. So what that gives me is up top I have a 2x minus 3. On the bottom I have an x and an x minus 2. All right? So it's just an extra or a minor little step you've got to perform before you can start graphing this and using the techniques we used about how to finding the vertical asymptotes, the holes, the horizontal asymptotes, and all that stuff. So this is a good review of all the stuff we did on Monday. So check it out. This is our function. Now I can go right to holes and say there's none. If you remember from Monday, only when a expression from the top and bottom reduced to 1, we have a hole. Vertical asymptotes here, I have 2. I have one at x equals 0 and another one at 2. Remember, those come from the denominator. X-intercepts, I plug in 0 for y, and I'm going to solve for x. If you do that, I'll let you try that because we did that on Fluency Tests, or not on Fluency Tests, but the week before, last week, we worked on finding the x-intercepts. Plug in 0 for y, and you solve for x, you're going to get 3 halves. The y-intercept, I'm sorry, I flipped that. So, sorry. X-intercept, you plug in 0 for y. I was looking at the y-intercept and I said x-intercept. So you plug in 0 for y and that's what gives you 3 halves. Plug in 0 for x, right? And something unique here happens. When we plug in 0 for x, let's see what happens. We get negative 3 up top. We get 0 times negative 2 on the bottom, right? So sometimes that happens when you 0 in the denominator is undefined. So in this graph, we will not have a y-intercept. We saw that on, I believe it was on Monday we saw that. It's impossible to have no y-intercept. It's also possible to have no x-intercepts, sometimes too. Okay, horizontal asymptote. Remember what that looks like? There's 3 cases you've got to know. For this function, now be careful. Sometimes it's tricky when the bottom is factored. You might want to distribute that that x back in so you can see it better. The top degree is smaller than the bottom degree, x to the first over x squared, and whenever that happens, it's automatically a horizontal asymptote of y equals 0. Look back at Monday's notes. There's 3 cases for the horizontal asymptotes, and you got to know those by heart. Okay, domain and range we'll do in a second. We'll come back to those. So let's start graphing everything here. We got vertical asymptotes at 0 and 2. So here's one at 0. Here's another vertical asymptote at 2. Okay. We said we had a horizontal asymptote at y equals 0. So we'll sketch that in as well. There's our horizontal. And now let's do some points. The only one we have is the x-intercept at 3 halves comma 0. So that's 1.5 comma 0. So I like this example, and I wanted to show it to you again. Just a reminder that sometimes we will cross the horizontal asymptote. In this case, we do. That's okay, as long as that doesn't happen way out towards infinity or way out towards negative infinity. Horizontal asymptotes describe end behavior. So that's what this graph will approach as x approaches positive infinity and as x approaches negative infinity. But sometimes we can cross it closer to the middle of the graph. Now technically there's no middle, but what I mean is not way out to the right and not way out to the left. Okay, so what I need to do here is I need to get some more points, right? I need to make a table. So I'm going to start this table, move this over a little bit. Let's go over here. Okay, so I first need to find out what's going on over here. So I'll plug in, I'm sorry, not that far, just to the left of 0, right? So I'm going to plug in -1 for x to see what I get. Now, when you do this, I've got two versions of the function here, two same versions. So you can plug -1 into either one of those, whichever one's easier for you to see. I kind of like always doing it into the factored one. That's just me. So if I plug in -1 in the numerator, I get -5. Then I get -1 times -3, right? So that's going to give me a -5 over a +3. So when x is -1, y is -5 over 3. Okay? So all I need that for is to tell me what's happening to the left side. Or on the left side here, -1 is -5/3. So that is 1 and -1 2/3. So I'm down there. What that tells me, and I could get another point, I could plug in -2 if I want, but the most important thing that tells me is that this leftmost branch is down in this bottom left corner of my graph. So something like that. Okay, now in the middle, between the two asymptotes, I have 1 point, but I've got to do a little investigation. I got to see, here are some options, right? I could have something that looks like that. I could have something that looks like this, right? It still has to pass the vertical line test, so I can't have anything that's like this, right? No, that won't work. So I'm going to plug in 1. If I plug in 1, I'll get enough information. So if I plug in +1, up top I get -1. On the bottom I get a 1 out front, and I get a -1 when I do 1 minus 2. So -1 over -1, that gives me +1. All right. So 1, 1 tells me my point's up here, and that's all I need. For the middle of this graph, I can kind of see what's going on. Remember, it has to pass the vertical line test, so my only option is to have this snake-like curve bending down like this. Remember, these graphs always have to approach your asymptotes, both vertical and horizontal. Okay. Now, last one, I need to find out what's happening over here to the right. So let's plug in 3. If I plug in 3, I get 4 minus 3, which is 1 up top. On the bottom, I get 3 out front. And I get 3 minus 2, which is 1. So that's 1/3 for 3. Again, I can always do more points. You want at least 1 point in each region, so you feel good about what's going on. So there's 3 and 1/3, or 3 comma 1/3. So I know this last branch is in the top right corner of my asymptotes. There's my graph. All right. So remember, no holes in this one because I didn't have any factors that reduced. Let's go back and do domain and range. So because there's no holes, the only thing I have to skip over are my asymptotes. So -infinity to 0, union 0 to 2, union 2 to infinity. And the range is going to be everything. Now this is a little unique because of this middle piece right here, right? That guy goes up and down forever. Remember, all 3 of these branches together make up one function. So because that middle piece goes up and down forever, the range is -infinity to +infinity. Yep, and that's our graph. So you can see after this first step, after giving these guys common denominators, the rest of the graphing techniques are the same. Finding all this information is the exact same, using the exact same techniques we did on Monday. So there's really no difference once you get common denominators and bring it together. Okay? So I have another example here. Feel free to work through it on your own. It's good practice. I'm not going to work through it right now just because it's really no different than the one we just did. This one does not have any holes. It has 2 vertical asymptotes. It's very, very similar. So good one to work through on your own. If you want to ever check the answer with me, feel free to shoot me the work of that answer and I'll tell you if it's right or wrong. But I want to show you the last skill we need to work on. So this is an application problem. Now this is actually cycling back to the first types of problems we worked on with the camp and the average cost per student at the camp and stuff like that. So we're going to do more now that we've done everything with these functions, solved them and graphed them and everything. We're going to work more on, we'll just work a little bit more with these applications. So it says the recording studio has fixed costs of $18,000 to lay down tracks for a new album. This includes studio time, equipment, musicians, etc. It costs $1.20 to make each CD. All right. So we want to write a rational function, a of x, giving the average cost per CD. All right. Now I got a, b here. I've got c and d over here. I just saw a little typo here that I want to fix. I meant to make that 25,000. So let's see if I can do that. Add another 0. All right. So I wanted to make that 25,000. Okay. So, all right. So the average cost function. All right. So first thing we need to do, because this is a rational function, and it says rational function in the problem, so that's kind of a nice hint. We know there's going to be some fraction aspect to this. Okay, so let's go up top and let's go back to first semester and come up with just a linear function that finds the total fixed cost, right? How much everything costs. It says recording studio is $18,000 in fixed cost, and it cost $1.20 to make each album. Now, because the $1.20 is the price that changes, or the amount that adds on and changes, we're going to put an x next to that. Now, first semester you would stop there. That would have been the linear function that represented the fixed cost and the cost per unit for this recording studio. Now, because I want the average cost, I just want to divide it by x, and that's what creates my rational function. So this function has all the asymptotes. It could even have holes. It could have all this stuff. Okay, so let's work on a few problems using this function. Letter B says, assuming the recording studio can only produce 25,000 CDs, what is the domain of a of x in the context of the problem? Okay, so what these problems are really going to ask us to do is, can we picture this graph, picture this function, what's going on without even graphing it? Okay, if you look back up at the original function here, because the denominator is just x, I'm going to have a vertical asymptote at x equals 0, and that's it. Okay. Now, as this graph goes to the right, because the company can't make any, or the recording studio can't make any more than 25,000 CDs, there's my max, right? So the domain is going to be, now technically, because we have a vertical asymptote at 0, we can't make 0 CDs. We're assuming here that they'll at least make 1. So let's start at 1. Okay, we'll bracket that because that can be included. And let's go all the way to 25,000 CDs. Now, that's the highest amount we know they can make, so we're going to bracket that. And there's your domain. Now, there's one little thing you had to add in here, though. We want to say integers only. They can't make a fraction of a CD. So my domain's got to be from the lowest number to the highest number, integers only. All right? All right. So now C, what is the average cost per CD if the studio makes 2,000 CDs? So now what we want to do is take that function we have back here, a of x, and we want to plug in 2,000 for x. The only thing you got to watch out for is this number that I give you, am I giving you an x value or am I giving you a y value, right? That's what you got to watch out for. So here, this is definitely giving you an x value. So I'm not even going to write a of x. I'm going to write a of 2,000, right? And that equals, we get 18,000 plus 1.2 times 2,000 over 2,000, right? And we got to type that into the calc. I actually forgot to find that value before I started doing this video. So I'll bring out my calculator really quickly and let's see what we get. Put a little approximation symbol there. I'm not sure if this is going to be a decimal or not. Okay, so let's see what we get. 18,000. We're going to add 1.2 times 2,000. And then we're going to divide it by 2,000. And we get 10.2. So, if they make 2,000 CDs, the average cost per CD is $2 or $10.20 per CD. All right. So I could give you any number there. If I want the average cost, you plug in whatever the number is for X and evaluate. All right. Now this is kind of a conceptual question. It says, as the number of CDs increase, what will the cost per CD approach? And how do you know? So, like I said before, it's kind of visualizing this graph without technically graphing anything. So, number of CDs is the x-axis. The average cost is the y-axis. We already said that there was a vertical asymptote at x equals 0, right? So, this problem, or letter D, as the CDs increase, that means as x approaches infinity, we want to know what the average cost is approaching. That's another word for the y value. Well, we talked earlier, end behavior in these graphs is the horizontal asymptote. So, if I look back at my original equation here, you might want to rearrange it for this horizontal asymptote part. But because the degree of the top and the bottom, the numerator and the denominator are the same, I get an x to the first over x to the first. I look at the ratio of the coefficients out front. Technically, out in front of the x is a 1. So the horizontal asymptote here is going to be 1.2. And that is what, so if I have my horizontal asymptote here, whatever this graph looks like, right? We said that there's only integers. That graph's going to go down, and the price is going to approach $1.20 without ever hitting it. So let's write a little sentence to summarize that. We'll approach $1.20 because y equals 1.20 is the horizontal asymptote. And we could even say, see if I can zoom on here a little bit. We can even say horizontal asymptote of A of X. All right, so it's a good summary cleaning this up. When I say how do you know, you got to explain yourself a little bit there. And like I said, the application problems, we've done a lot of work with these, so it's basically answer questions, thinking about the graph without ever really graphing it. Okay, so your homework today is a worksheet posted on Schoology like we've done for the past few nights. Just a heads up, next Tuesday, that will be the next Bronco day, we are going to have another take-home assessment, Fluency Test 6. It's going to be made up of a few different things, a worksheet doing some problems. There's also going to have a video in there and some multiple choice probably on Schoology. So log in Tuesday or go to Schoology on Tuesday and you'll see the assignments there with detailed instructions on how to do it. And those take-home assessments do go in the summative category. So you notice there's no review for this. Your review is just the past homework assignments and the work we've been doing. Make sure that's all done and you should do fine on this fluency test. So guys, have a great weekend. Happy Easter if you celebrate it, and I will talk to you next week. Oh, by the way, always remember there is a office hour today from 10 to 11 a.m. If you want to stop in and chat, I'll be there.